I'm Dr. Samuel Allen Alexander, mathematician and philosopher, still here. Actually, I'm usually asleep at this hour. I'm in Southeast Asia, so it's about 3 a.m. right now. But I was having insomnia, and I was thinking about this paper that I'm working on. During the last live stream, I was unsatisfied with my explanation of why this triviality condition is a triviality condition, and I thought of a better way to go about it. So, in view of the lemma trivial lemma, we're primarily interested in infinite S subset G. I might even get rid of that lemma. The main technical result of this paper is a theorem which says that if infinite S subset G satisfies the convexity axiom and the IAP axiom, and if S is not too trivial, then S locally satisfies the Knight-Darwin law. What do we mean by not too trivial? We mean not competition trivial, which we define in the following definition. Because this definition is rather complicated, it might not, at first glance, look like a triviality condition, but we will argue that it is. But we'll argue below that this condition is strictly more limiting and hence the sets which satisfy it are more trivial than a simpler triviality condition, than a certain more straightforward triviality condition, than a certain more straightforward condition which is manifestly a trivialness condition, which is manifestly one of trivialness. Definition. If S is a subset of G, we say S is competition trivial if the following condition we say S is competition non-trivial if the following condition holds. If we say S is competition non-trivial, if there exists an infinite directed path u1, u2, ... if I just if there exists an infinite directed path boundary to dot dot in S whose members we think of as heroes, and an infinite directed path W1, W2, dot dot in S whose members we think of as villains, such that vi not equal to wj for all ij. If S is not competition non-trivial, then S is competition trivial. In order to justify calling this a triviality notion, we will place it strictly between. In order to justify calling this a triviality condition, we will observe that it falls between two other conditions which are uncontroversially triviality conditions. Definition. Suppose S subset G itemize S is totally trivial if S contains no infinite directed path. S is mostly trivial if there exists an infinite directed path P in S such that S backslash P is totally trivial. Lemma. Observe that it is more strictly than, it is more strictly limiting than a condition which we call mostly trivial, defined below. Whose status as a triviality condition is, we believe, uncontroversial. Lemma. For any S substitute G, if S is competition trivial, then S is mostly trivial. Um, Except that's not correct. No, it's the opposite. If S is mostly trivial, then S is competition trivial. And that's what we want, right? Because that says that the set of wait. Okay, there's two different things. There's what we want and there's what's true. And hopefully those are the same thing. Now, is this lemma true? I believe it is, if it's mostly trivial. There's just this infinite vector dot P. Wait, no. This. To say that to say that that lighting's not very good. I don't want to. I realize that the lighting's terrible for the stream. But I don't want to turn on the lights because, like I said, I'd love to get to sleep. Suffering from insomnia. Now, in order to justify calling this a triviality condition, we'll observe that it is more strictly limiting. Competition non-trivial means you can find the heroes and villains. Competition trivial means you cannot find the heroes and villains. Such that no member of S is both a hero and a villain. Just to make the definition of competition non-trivial a little more colorful. So to say that it's competition trivial means that you can't find heroes and villains. That means that every hero path chops off the villains. Any way you assign heroes, annihilates the villains. Any way you assign heroes, you annihilate villains. In other words, for every infinite directed path P, S backslash P is totally trivial. For any S subset G, if S is competition trivial, then S is totally trivial. And that is what we want, right? That means, yeah. But the problem is we haven't assumed the hypotheses needed for Koenig summa. And we'd rather avoid assuming those hypotheses just for the sake of this particular lemma, because they're not needed for the actual thing that we care, the actual main proof. So biologically, we care about graphs G where Koenig summa holds. The main proof doesn't require that machinery. But this justification of a name requires the machinery. See, what we want to say is that Koenig's lemma G contains some infinite path P if S is competition trivial, then it is impossible to consider the members of P to be heroes while also considering a different infinite path Q to consist of villains without some overlap, without some member of P also being a villain. So we should start there with saying assume S is competition trivial. By competition triviality, it is impossible to consider the members of P to be heroes while also considering a different infinite path in Q to consist of villains without some member of P also being a villain. Such paths Q are exactly paths in S backslash P. So S backslash P has no infinite directed path, i.e. is totally trivial. So S is, we don't want to say totally trivial here, we want to say mostly trivial. So S is mostly trivial. The problem is we don't have the hypotheses for Koenig's lemma. For now, I'll just make a note. We don't have the hypotheses for Koenig's lemma. The thing is, we mainly care about biological graphs, and biological graphs do have the hypotheses for Koenig's lemma. And the hypothesis for Koenig's lemma makes this lemma work. Now, this lemma is only included in order to justify a name. So we don't want to weaken the main theorem later on just for that purpose. Oh, what an annoyance. This is not a mathematical annoyance. It's a narrative annoyance. Anyway. We argued above that the convexity axiom and the IAP axiom are plausible properties which we should expect species to satisfy. We would further argue that if S sub G is a species and S is infinite and if S is non-trivial, then S should oh, this is, yeah. I'll just delete this. Oh, well, let's comment it out for now. Comment out that whole paragraph. You can delete this earlier justification attempt. The main theorem is, so we, instead of talking about two mutually exclusive paths, we say S is not competition trivial. Then it satisfies the Knight-Darwin law. Yeah. Now, the following, we now state a weak version of the main technical theorem of the paper, whose proof is significantly simpler. We do this because it sheds light on what's going on. We do this because we feel the easier, weaker result makes it clear what is happening after the easier, weaker result. We will proceed to the full result, which is stronger but has a more complicated proof. Proposition to be strengthened and theorem and theorem low. Let us substitute and assume. Let's just copy paste here. S is not mostly trivial. Then S locally satisfies the Knight-Darwin law. Proof. Remember, not locally trivial. Well, mostly trivial means there exists an infinite directed path P, such that S backslash P is totally trivial. So, assume the hypotheses. Assume U1, U2, dot dot, is an arbitrary infinite directed path in S. We must show that some UI has more than one parent, has multiple parents in S. Since S is not mostly trivial, S backslash U1, U2. Let's give this a name, P equals U1, U2, dot, dot, dot. Since S is not mostly trivial, S backslash P is not totally trivial, unless there exists an infinite directed path, Q equals V1, V2, dot, 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 in S backslash P. Now, since V1 has infinitely many descendants in S, namely V2, V3, dot, 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 by the IAV property, v1 can S cannot contain S contains less than infinity many non-descendants of v1. Thus, there is some I such that ui is a descendant of v1. The IAP axiom guarantees S contains less than infinitely many non-descendants of v1. Thus, there is some I such that ui is a descendant of v1. Thus, there is a directed path x1 dot dot xk x1 dot dot xn in S, well, in G, such that x1 equals v1 and xn equals ui. By the convexity axiom, each xj is an S. Since xn equals ui is in P, there exists, well, rather, let k be minimal such that xk is in P. There is some such k, let's make it n, since xn equals ui is in P. Say xk equals u L. We don't want L to be 1. Unless there is some I such that ui, unless there is some I bigger than 1 so that ui is a descendant of v1. Unless there is a directed path by the convexity axiom each xj is in S. Let k be minimal such that xk equals ul for some L bigger than 1. There is some such k that's ranked n since xn equals ui and I bigger than 1. Then ul has two parents. Then ul has parents ul and x sub k minus 1. Note k bigger than 1 since x1 equals v1 is not in P. Thus, UL has parents UL minus 1 and xk minus 1, which must be distinct since UL minus 1 is in P and xk minus 1 well, what if xk minus 1 equals u1? That is a possibility. So you want to say that by minimality of k, xk minus 1 is not in P. The problem is, it could be in P, it could be u1. And L could be 2. Is it... Would it be as simple as on line 436, changing I bigger than 1 to I bigger than 2? And then let k be minimal such that xk equals ul for some L bigger than 2. There is some such k lesser equal to n since xn equals ui and I bigger than 2. Not k bigger than 1 since x1 equals v1 is not in big P. Thus ul has parents ul minus 1 and xk minus 1, which must be distinct since ul minus 1 is in big P and xk minus 1 is either in S backslash big P or possibly is equal to no, that doesn't solve it because now xk minus 1 could be u2. Oh man. Let's change those 2's back to 1's. Oh, I love math. Okay, I'm gonna have to come back to this proof. So close. So close. I mean, I'm pretty sure that the theorem is true. This is supposed to be the easy version. Better not make it too much more complicated or else it's no longer easier than the main theorem. Well, it's still easier than the main theorem by far. The main theorem is complicated as all get out. Good grief. I think I can simplify the proof of the main theorem by using mathematical induction. I'm going to have to work on that as well. So, note to myself, we want to say that well, must be distinct since xk minus 1 is NP and ul minus 1 ul minus 1 is NP. And we want to say that xk minus 1 is in S backslash P. But the problem is the choice of K, the I bigger than 1 part in the choice of K makes it so a priori xk minus 1 could be u1. Yeah, I'll stop there. Git commit insomnia inspired revisions concerning triviality. Okay, I'm gonna go back and try to get to sleep. I'm Dr. Samuel Allen Alexander. Please like, comment, and subscribe. I'll see you in the next video.